Hello guys, let us today see eigenvalues and eigenvectors. Already we have seen the definition of what is meant by an eigenvalue and an eigenvector. Let us recall. See, if we are having a square matrix capital A of order n by n, and you multiply this A by a column matrix X, and you are multiplying by some value, some scalar lambda to the X, and you get the same result. Multiplication by a matrix and multiplication by a scalar are equivalent, both are equal. So such a number lambda we call as eigenvalue of that matrix A, and the corresponding vector X is called an eigenvector. One thing we should note that this X is a non-zero thing. If X happens to be 0, then obviously left side is 0, right side is 0, they will match. But without having X 0, when we are having A into X the same as lambda into X, this lambda is an eigenvalue and X is an eigenvector of the matrix A. So let us solve a few examples based on this particular. Our first question is 5 an eigenvalue? Is 5 an eigenvalue of this matrix? So let us call this matrix as our matrix A, and we want to check whether 5 is eigenvalue of this matrix or not. The technique with us is, what we do is, we construct a matrix lambda I minus A. This matrix we usually call as characteristic matrix. We'll come to it later. So this lambda I minus A, and we check its determinant. If the determinant happens to be 0, we say lambda is eigenvalue. And if the determinant is non-zero, we say lambda is not an eigenvalue. So what we have done is, I means identity matrix. So what will happen is, identity matrix has entry 1 along its principal diagonal, and rest all the entries are zeros. So the same way what you observe, this 5, 5, 5, meaning lambda appears only on the principal diagonal. Elsewhere there is no blue entry as you are watching. So the lambda appears only on the main diagonal. Now minus A means every entry of A is negated. We are subtracting. So what happens is minus 6. This was the entry of A which we subtracted here. Earlier it was minus 3. We subtracted it from 0. It becomes plus 3. Earlier it was plus 1. We subtracted, it became minus 1. So same way we have written this particular characteristic matrix and we are finding its determinant. Now what happens is, this is minus 1, the rest of the entries are as they are, and now we calculate it. Minus 1 into this particular product minus this product minus this entry 3, minus 3 into minus 1 is 3. From that we subtract the product of minus 2 and minus 5, that is 10, and plus this entry. This is itself a negative entry, so we will have minus here, and to that we multiply by the product 6 and subtract 10, minus 10, so it becomes plus 10. And ultimately what we find is, this is 15 plus 21 minus 16 equal 20, which is a non-zero entry. So what we can decide, this 5 is not an eigenvalue of A. The question was, is 5 an eigenvalue of the matrix? And what we did was we prepared a characteristic matrix, we found its determinant, and what we observed was the answer was non-zero. The answer being non-zero, we are saying that 5 is not an eigenvalue of A. Let us move on to the next question of the similar type. Question says, find the eigenvalues of A. So to find the eigenvalues of A, now I think we are quite familiar with the characteristic equation. We take the characteristic matrix, that is lambda I minus A, find its determinant and equate it to 0, solve it and get the values of lambda. So we are getting, this is lambda minus 3, as I have said earlier, lambda will appear on the principal diagonal and every entry of A is negated. So I got lambda minus 3, minus 2, minus 3 and lambda minus 8. Solving it, I got the product of these two. It was lambda square minus 11 lambda plus 24, and from that we subtract this product, that is 6. Ultimately we reach to lambda square minus 11 lambda plus 18 equal to 0. We want product plus 18. Whenever we want product plus, the factors must be both either positive or both negative. And the second check is this particular entry. The sum of the two factors must be minus 11. When sum will be minus? If both are minus. So it's very natural that minus 9 and minus 2. Product is plus 18, sum is minus 11. So I got this. And equating each bracket equal to 0 will get lambda equal to 2 or lambda equal to 9. These are the eigenvalues. Now let us move to third type of question. The question says, is this vector, column vector, an eigenvector of A? A is given, vector is given, and they are asking us whether this is an eigenvector. When to say this is an eigenvector? So if multiplication by a matrix equals multiplication by a number, then we say it is an eigenvector. So we took A multiplied by X, this is the product, 3 ones are 3, plus 6 into minus 2 I got minus 12, plus 7 into 1 I got plus 7. Same way I calculated here, I got minus 2, 4, minus 2. I find minus 2 is a common one. I've taken it out and inside we are left with same vector. So very naturally this vector is an eigenvector. So our conclusion is x equal to 1 minus 2, 1 is an eigenvector of E. Now next question again on the same lines. Question is asking you, is this an eigenvector of this matrix? Only the thing is, this number is not an integer. It is a surd as you are watching. Root 2 plus minus 1. So rational plus irrational. We call it as a surd. Again on the same lines, we'll multiply A by that x. So A into x we have. We got this kind of matrix as you're watching. But how to take the thing out? If I simplify it, I got this. But there are no signs I'll get this back. So what I did was, this lower entry is 1, the second entry. So if I divide by this particular, if I take this common, what do I get in the upper part? So that calculation is done in rough here. You can see here it was minus 1 plus 2 root 2. To that I divided by 3 plus root 2. You know, I have to rationalize the denominator. So I multiplied by the rationalizing factor 3 minus root 2 in the numerator as well as in the denominator. If I multiply in the denominator, I have to use the rule a plus b into a minus b, that is a square minus b square. 3 square is 9, root 2 square is 2. So ultimately I got 7, that is written over here. And I multiplied these two brackets, you can see, minus 1 into 3. Then I have minus 1 into minus root 2 making it plus root 2. Then I got 6 root 2 here, and this 2 multiplied together gives me minus 4. So this was minus 7 plus 7 root 2. So if I split the terms, 7 by 7 gives me 1 and the minus sign is written. This plus sign is there, 7 gets cancelled and I got root 2. So this entry is minus 1 plus root 2 that we have noted here. So what you observe, a into x is the same as number into x back. So what this means, this particular matrix is nothing but the eigenvector of that matrix and the corresponding eigenvalue is this particular number, that is 3 plus root 2. Now let us move to one more question of the same kind. Is this an eigenvector of A? And if so, find the corresponding eigenvalue as we did here. So we multiplied A to x. You can see 3 4s are plus 7 minus 3s are plus 9 1s are, it becomes a 0. Again here you watch, this becomes minus 16 plus 15 plus 1, again a 0. And talking of the last even, you are getting a 0. And whenever you get 0, 0, 0, you can say 0 can be taken out. And I can say it is multiplied to this particular matrix. See here, I am not saying x is 0. What I am saying is eigenvalue is 0. So a into x I can write as 0 into x back. Means x is eigenvector, but the corresponding eigenvalue is lambda equal to 0. I suppose you are getting it. And one more thing we have to keep in mind, whenever eigenvalue is 0, that matrix is never invertible. Inverse does not exist. So this is the thing we have. One more question. The question says, find a basis for lambda equal to 4. Find a basis for lambda equal to 4 of a equal to 10 minus 9, 4 minus 2. So what do? They have given us lambda equal to 4. So we solve the equation lambda I minus a times x equal to 0. We'll call it as homogeneous system of equations with putting lambda equal to 4. So how do we solve it? We'll use Gaussian elimination method. We consider 4i minus a because you know lambda, so better you put its value. So 4i minus a. If lambda is not known, we call it as lambda I minus a, but here we know lambda is equal to 4. So 4i minus a, so what it will be? It will be certainly, you can see 4 minus 10. Along the principal diagonal, we have our lambda. So 4 is there. 4 minus 10 makes it minus 6. The next entry was minus 9. So 0 minus minus 9 makes it plus 9. Next is 0 minus 4. You can see minus 4 here. And along the diagonal, you have lambda. 4 minus minus 2 makes it 6. What do you observe? Both are multiples of 3 here and both are multiples of 2. So it's better you multiply R1, the first row, by minus 1/3, second row by minus 1/2, which gives you 2 minus 3, 2 minus 3. Same rows we are getting. So it's better we subtract the first row from the second row. So 2 minus 2 will be 0 here. Same entry we are subtracting, so 0 here. Once you get this kind of format, you rewrite the system. If we rewrite the system, what I got here is 2x minus 3y equal to 0. Only one equation I got in hand. And the variable y is a free variable here. So I put y equal to t. And you can see what is t? T is any real number. Putting it back in our first equation, what we get is 2x is equal to 3t. So x will be 3t by 2. Now this is our solution. Value of x is 3t by 2 and value of y is t. So this is our solutions. We have to write our solution space. Solution space is known as eigenspace. So we denote it by E of lambda equal to 4. So E of lambda equal to 4 is equal to, we have to write the entries in a column. So first entry is 3t by 2, second entry what is t, and what is t? T is a real number. Now, if I want fraction to be out of the matrix, so I have taken t by 2 out, common. Inside I'm left with 3, and here I have to write 2 because twice t by 2 is nothing but t. So I got a fixed vector as a matrix, and this is nothing but the basis. So basis for E of lambda equal to 4, E is missing here. So this particular, so basis for E of lambda equal to 4 is curly bracket column matrix 3, 2. So this is known as basis for the eigenspace. Why to call it as basis? Because all the eigenvectors will be multiples of this kind of vector. So now one more question let us deal with. Here lambda is given to be minus 2, and we are asked to find the basis for eigenspace of A equal to this matrix. So as we did earlier, same thing we are going to do. We'll put lambda equal to minus 2 and solve the homogeneous system. So we solve the system minus 2i minus a times x equal to 0. Here, because lambda is negative, I have shown how to calculate it once again. Actually, you all know, but this being a 3 by 3 matrix, I have solved it. So you can see minus 2i minus a. So what happens is, along the diagonal you will find minus 2 everywhere, and from that we are subtracting a's, entries of a. So what you observe, I would like to keep this a in front of us, okay? Then minus 2 minus 1, then along the diagonal you see minus 2 plus 3, and lastly you have minus 2 minus 1, so directly I have written 3 here. Rest all entries you see are negated, zeros as they are. There was minus 1 here, so it becomes plus 1. This was a 1, it became minus 1, 4 became minus 4 now, and minus 13 has turned to be 13. So this way we calculate our characteristic matrix. Next, to solve this homogeneous system, what we do is we use Gaussian elimination. And what we need to do is we have to convert the matrix in row echelon form. So what we did was this entry being negative, and what we observe is there is minus 4 again. So it's better if I subtract r1 minus r3. So it will be minus 3 plus 4 will give me plus 1 here. That is the strategy. So you are observing minus 3 plus 4 gives me a 1. This is 0 minus 13 gave me minus 13, and 1 minus minus 3 makes it plus 4. Remaining rows I have written as they are. Now, observing this 1 and this is minus 1. If I simply add the first row here, this will turn into 0. So R2 plus R1 will bring a 0 in this place. And one more, this being minus 4, if I add 4 times 1 to that, it becomes a 0. So in the third row, we are adding 4 times first row. So first row as it is, minus 1 plus 1 makes it 0. 1 minus 13 makes it minus 12. 0 plus 4 is a 4. Next you see, minus 4 plus 4 is a 0. 13 minus 4 times minus 13. Extremely sorry. 13 plus 4 times minus 13. So I have to subtract it. So it will be minus 52. This being in the table of 13, you know, this will be thrice 13. And lastly, minus 3, and we'll have plus 16, making it plus 13. So you can see 13 and 39, they are in the same table. That is helpful to us. 4 and 12, they belong to the same table, and we take its advantage. We multiply the second row by minus 1 by 4, third row by minus 1 by 13, so that we get this kind of matrix you are watching. Now, the second and third row are identical. So what we'll do is, from R3, let us subtract R2, so that we'll get bottom row 0. Once we reach to such kind of thing, it's similar to the row echelon form. If I make this 3 into 1, it will be row echelon, but I don't need it. So what I'll do is, I'll rewrite the system. Rewriting the system, we get 1 times x minus 13 times y plus 4 times z equal to 0. Next is thrice y minus z equal to 0. Now you don't have any clue for z, what z will be. So that means z is free and we'll assign it some t. So put z equal to t belongs to r. Now rewriting, back substitution helps us. If I back substitute, I'll get 3y is equal to t, meaning y is t by 3. And put the values of y and z back in the first equation so that x will be t by 3. So we get our solution. So that solution space we denote by E of lambda. So we have written E of lambda equal to minus 2 equal to. We wrote this in column matrix format. So in the column matrix, value of x is t by 3, that of y is t by 3, that of z is t, such that t belongs to r. Now if you want to be fraction free, take the fraction out. So t by 3 is taken common and inside I'm just left with 1, 1, 3. And I have to mention what is my t. T is a real number. So what is the basis then? So you can see the fixed vector we call always as the basis. So basis vector is 1, 1, 3 as a column matrix. So this is the basis for eigenspace. Hope this was fruitful. Solve questions based on this. What we saw today was how to find the basis for eigenspace. Here also we have seen how to find basis for the eigenspace. Here we have seen how to show the given vector is an eigenvector and how to find the corresponding eigenvalue. This question also was of the same pattern. Given vector, we had to decide whether it is an eigenvector or not, and if so, how to find the eigenvalue corresponding to that vector. Here we have simply shown that the vector is an eigenvector, but now you can guess what is the corresponding eigenvalue. Yes, minus 2 is the corresponding eigenvalue. Here we have seen how to find the eigenvalues of the given matrix. And in the beginning, actually we began with whether the given number is an eigenvalue of the given matrix or not. When to say the given number is an eigenvalue. For that, we equate the determinant of characteristic matrix to 0. If for that particular value determinant happens to be 0, we say it is an eigenvalue. If not, we say that it is not an eigenvalue. So hope you'll keep practicing this kind of questions. Thank you. Goodbye.